Hello, welcome. Today we will deal with statically indeterminate problems in axial tension and compression. I have prepared 3 examples, dividing this course into 3 parts, so in each part I will solve one example. Welcome. Example 1. A 2-step rod has been permanently fixed at ends A and D and is loaded with forces as shown in the diagram. Calculate the reactions at the fixings and indicate where the largest stresses occur in the rod. We have the ratio of the cross-sectional areas of parts AC and CD. Area A1 is twice as large as area A2, and we have the ratio of Young's moduli of these 2 parts of the rod. So the task is statically indeterminate because we have only one effective equation of static equilibrium available, which is the sum of the projections of forces along the x-axis, and we have 2 unknowns. We have an unknown reaction in one support and another support. The sum of moments doesn't help us, the sum of projections on the other axis, that is, the y-axis, doesn't help us either. So here we will use the geometric condition, which in such standard tasks, if the rod is supported from both ends, states that the total elongation of this rod is equal to 0. Which then reduces to the sum of the elongations of all segments, about which I will speak shortly. So what we can do first is calculate the sum of the projections on the x-axis, which should equal 0. The forces that have a direction consistent with the accepted direction of the x-axis are positive, so Ra plus 15 minus 20 minus Rb equals 0. Well, we could also rearrange and move Ra to one side, but for now it is just one equation with 2 unknowns, so we can't do anything with it yet. So we will use this geometric condition, meaning that the total elongation of the rod is equal to 0. The total elongation of the rod is the elongation of these 3 characteristic intervals that I marked in the diagram, which is delta LAB plus delta LBC plus delta LCD. A characteristic interval occurs when either a new force is applied to the rod or the cross-sectional area changes. And here, both the cross-sectional area changes and a new force is added. This can also happen, so we have 3 characteristic intervals here. So let's recall the formula for elongation. It is the force in this segment of the rod times the length of this segment divided by Young's modulus times the cross-sectional area. So let's write down the forces in the intervals AB, BC, and CD. The force in the interval AB, looking from the left side, well, the interval AB is as if the force 15 kN only starts in the interval BC. We do not see it in the interval AB yet, as if we are infinitely close to it. So from the left side, we only see the reaction Ra. It is positive because it is in line with the direction of the x-axis. In the interval BC, we see both this force Ra and the 15, and they sum up, both are positive. And in the interval CD, we see all 3 forces, except for the reaction Rb. Of course, we could do the same from the other side, so here there would be only Rb in interval CD, here the 20 would come in, and here the 15 would come in, and we would not reach Ra. So this is a degree of freedom. Well, I started from the left side. Anyway, either by going from the left side, we do not reach the reaction Rb, or by going from the right side, we do not reach the reaction Ra, which means we will have one unknown in this equation. That's what we wanted. So the force in the interval CD is Ra plus 15 minus 20, summing up Ra minus 5 Kn, of course. Now we substitute these forces NAB, NBC, and NCD into this formula, so we calculate the sum of elongations. The force in the interval AB times the length of this interval, 1 meter, divided by Young's modulus of the first material and the cross-sectional area of this part of the rod, that is A1, and so on. I have substituted all of this. Now from the problem statement, we know that A1 is 2 times A2, and E2 is 2 times E1. And now I substitute this. For A1, 2 A2, and for E2, 2 times E1. And I multiplied the brackets above. Now let's multiply by this part of the denominator, so it cancels out. That is E1 times A2. And we immediately separate these fractions. 3Ra over 2, that is 3 halves Ra, plus 45 over 2, that is 22.5, and so on. RA on the left side, the rest on the right. Divide by 3.5, comma, we have the reaction result, and at the support A, it is minus 4.286 kN. This minus indicates that I assumed the direction incorrectly, but that's okay. This reaction has the same value, 4.286, comma, but with the opposite direction. This minus here tells us that. Now we can go back to our sum of projections on the x-axis and substitute for RA minus 4.286 kN and calculate RB. So RB would equal that. So we have the reactions at the supports, and we can now focus on the topic of which interval has the largest stresses. So we calculate the numerical values of what we previously wrote in symbols. So NAB was RA, which is calculated. NBC is RA plus 15, that's it, and NCD. We also substitute the value of RA. Although it is not necessary, we can draw a graph of normal forces. There is no problem. Now the stress is the force in the rod interval we are interested in divided by its cross-sectional area. So the stress in the interval AB will be the force from interval AB minus 4.286 kN divided by A1, that is by that cross-sectional area. And we will also substitute that A1 is equal to 2 times A2. So we will express all these stresses in such a form. We will take that numerator as if outside the fraction, and it will be multiplied by 1 divided by A2. We will express all of them this way. It will be easy for us to compare which stresses are the largest in which part of the rod. So NBC will be divided by A1. A1 is 2 times A2. 10.714 divided by 2 is 5.357 multiplied by 1 over A1. And the stresses in part CD will be 9.286 divided by A2. So here we won't substitute. And we have the result. Now, which stresses are the largest? Well, those in interval CD. Here the sign does not matter. For instance, if there were stresses in interval AB, let's say minus 11 divided by A2. Here there isn't really a final unit yet. Well, the stresses will be in pascals, but we haven't set the cross-sectional area. We also still have this expressed in terms of this cross-section, but all these stresses are expressed in the same form so we can compare them. And what I wanted to say is that if there were a negative value greater than this positive one, then the greatest stresses are those in absolute value. Similarly, if we had the dimensioning of the rod, we look for the greatest stresses in terms of absolute value, unless there were a division between tensile and compressive strength. Okay, so the greatest stresses are in the range CD, which is quite obvious, because here we have the smallest cross-sectional area, and the smaller the cross-sectional area, the greater the stresses in this part of the rod. Well, it also naturally depends on the force. Okay, we can move on to the second example. And here I've also drawn a stress graph times 1 over A2. We can represent this on a graph. I recommend our other productions. I encourage you to subscribe to the channel. Then you'll be up to date with new materials from EduPanda, which will be more and more. Thank you for your attention. Warm regards. Goodbye.